Hello, I'm your airline pilot today, and we're going to learn how to solve systems of linear equations in three variables. Let's get started. Up to this point, we've solved systems of linear equations with two variables, x and y, and now we're going to take it into the three-dimensional world and solve linear equations that involve three variables. This can get confusing, but if you word things and phrase them the same way I am, it'll really make things more straightforward. So let's get started. First, we're going to define a linear equation in three variables, and it is an equation that looks like this. Okay, and note that they're just saying to A, B, and C cannot all be zeros, otherwise it wouldn't be in a linear equation in three variables, it would suddenly be in two or one variable. And then it goes on to show you what a system of three linear equations would look like. And remember, they're all working together, and your x and y and z coordinates must be the same for all three equations, making all three statements true then, which is the definition of a solution of a linear system. So a solution of a linear system is an ordered triple x, y, and z whose coordinates make each equation true. Ordered triple, think of where that's coming from. We're used to just two coordinates, x and y, and we call it an ordered pair. So now it's called an ordered triple. All right, so let's actually look at what a system graphed in three dimensions would look like. And here's a nice picture of the three possibilities. So the first system graphed in three dimensions, remember it's three-dimensional space, so you have three planes. And if your planes intersect in a single point, that means you have one value for x, y, and z, and there's the coordinate where it's located. Infinitely many solutions means your planes intersect in a line or in the same plane, and that would be sort of like the concurrent lines where one landed right on top of each other. So this one equation would be produced out of the three linear equations. When you solve them, it would really be like it looked like one equation. It was the same equation. No solution would mean planes have no common point of intersection, and you'll see that happen later on in an example where you have something improbable come up when you're solving the linear system, and then at that point you would say there's no solution. But here's how that would come into play. Here you have two planes that are intersecting, but the third one's not involved, and so that's not a solution for the whole system. Here again, two planes that are interacting, but not three planes interacting. And then you could have three parallel planes, and that again would be no solution. There would be no coordinate triple x, y, and z that would make any three of these exist. So you can read the key concept below, and the elimination method is what we're going to be using to solve a three variable system. And it goes through the steps here, and they won't make much sense until we actually start doing it. But your first step is to rewrite the linear system of three variables in a linear system of two variables. So what we're going to end up doing is eliminating one of the three variables. Then you solve the new linear system that you wrote for both of its variables that were left over. And your third job then is to substitute the values found in step 2 into one of the original equations to get the third variable. So let's get started with an example. Here's our one main big example that we're going to do together. Here you see your system of three equations. Notice your variables are x, y, and z. Your first step is to choose a variable you want to eliminate. It can be x, y, or z, it doesn't matter. In this case, I'm going to look at equation 1 and equation 3, and I'm going to try to get rid of the x's. So just as with any elimination problem, you can see my coefficients of x are not matching. And so what I'm going to do is I'm going to multiply equation 1 times 2 to get rid of that x. To keep myself straight, though, I always write down what I'm eliminating. So my goal is to eliminate x. So I start off and I make sure I'm always notating what I'm doing because you can confuse yourself here. And this is for your notes as well. So I am going to add equation 1 and equation 3 after I multiply equation 1 times 2. And my new equation 1 then, or when I redo it, is 4x minus 2y plus 12z equals negative 8. Don't forget that last one. And really this is just your equation 1. And right below it I'm going to write equation 3 over again. Negative 4x minus 2y plus 5z equals 9. And you're going to add these two together. And you know me, I like the big plus sign out front. So when I'm adding in columns, and I'm going to keep it in red here, I'm going to do 4x minus 4x. Well, you've just eliminated x, which is what your goal was. Negative 2y plus a negative 2y is a negative 4y. And 12z plus 5z gets you 17z. And negative 8 plus 9 gives you 1. And now I'm going to call this thing new equation 1. You're going to see this over and over again. So we're going to rename this equation new equation 1. Well, I need another equation. Remember, if you have two unknowns, two variables that you need to solve for, in this case y and z, I need a whole other equation, two equations for two unknowns. So what I'm going to do is I'm going to use equation 1, and I'll erase what I had there before. I'm going to use equation 1 and equation 2, and I'm going to get rid of x's again. Your eyes eliminating the same variable because I need two equations without an x. So in order to do that, and my thing is being picky, won't let me erase this, I'm going to multiply this by a 3, so I'm going to make this a 3 if I can, just right over the top. So I'm multiplying now equation 1 by 3, and so I will end up with 6x minus 3y plus 18z equals negative 12. That was equation 1 multiplied by 3, if you wanted to write that. The second equation, equation 2, is 6x plus 4y minus 5z, and that equals a negative 7, and that is equation 2. Then, in order to eliminate x, I need to subtract the columns. 6x minus 6x is 0. Negative 3y minus 4y is negative 7y. 18 minus a negative 5 becomes 18 plus 5. So now we are at a 23z. And then we end up with negative 12 minus a negative 7, which is negative 12 plus 7 is now a negative 5. And I'm going to call this one new equation 2. So now when you look at it, I have two equations with the same variables, two equations, two unknowns. I can solve these using the elimination method again and eliminating the y or the z to get, the y or the z. And so what I want to do, I'm just going to pick, and again, every problem is going to be different, and you're going to do it in a different way. But I'm going to choose to eliminate the y's from these two new equations. So the first new equation 1, I'm going to need to multiply by 7. So maybe I can write, and I'll go up here, 7 times new equation 1, just for your notes. Sorry if you can read that. And so 7 times new equation 1 will become, maybe I'll write it here then. Careful your notes. I'm going to put a 7 there. I get negative 28y plus 119z equals 7. Then I'm going to look at my new equation 2, the one right here, and in order to get this to be 28, I need to multiply by 4. So for your notes, we will write 4 times new equation 2, and I'll put a 4 here. And so I end up with negative 28y plus 92z, and that equals a negative 20 after you multiply the 4 times the negative 5. So now it's sort of hopefully coming together for you. You see you have two equations and two unknowns, and you've just eliminated the y's as soon as you decide to subtract these two equations. So subtract the two equations, and you will see your 28 y's cancel each other. They're opposites. You are left with 27z. Well, I want to change my color. Okay, so say 27z equals 27. And all of a sudden, this problem has become a little bit better. So we already know one of our coordinates for our triple, and that is that z equals 1. So now you can substitute that value either into new equation 1 or 2. You could do it to these, but those numbers are huge. And so I will substitute z equals 1 into, well, let's pick this one because it looks the simplest. So I will take new equation 1, new equation 1, and I'm going to substitute in z equals 1. So we have negative 4y plus 17z, which is 1, and that equals 1 when we solve it. Our next line then would be negative 4y equals a negative 16. And finally, we get y equals 4. So now we have 2 down, 1 to go. So you can substitute these two new variables that we found into any 3 of these equations. And so I will just pick for ease, I guess, number 3. Yeah, that looks good to me. Let's go for that. So we'll take equation number 3. And so I have, I'll do it down here, negative 4x minus 2 times y plus 5 times z, which is 1, equals 9. Clean that up. Negative 4x minus 8 plus 5 equals 9. Let's see, negative 8 plus 5 is a negative 3, and then I add 3 to both sides. So I get negative 4x equals 12, and then dividing by negative 4, I get a negative 3. So x is a negative 3. So your Pythagorean triple then you should write out, just as we did a coordinate pair, we should write out our solution to that Pythagorean triple, and I want to do it in a pretty color. And I wonder if a rainbow would work nicely. And so we can do, oh, it doesn't work at all. Negative 3, y was 4, and z was 1, and our solution is that coordinate triple. You could also check that, just like you could before, by plugging those numbers into any 3 of the equations and making sure they work. All right, here's a guided practice problem. I'm actually going to solve it the long way and record the whole time. But if you feel like you want to try it on your own, just go ahead and skip to the end where I get the answer for you. But in the meantime, I'm going to start solving the system of 3 equations. The first thing to decide, remember, is which variable do we want to eliminate. And just looking at it, and just to be different than the first one, I'm going to eliminate y. Now, if you choose to eliminate it another way, your process will look totally different along the way, but your final answer will be the same. All right, so I am going to write down what I am eliminating so I don't forget, and my job right now is to eliminate y. So I am going to take equation 1 and equation 2, and clearly I need to multiply equation 2 or equation 1 by 2 in order to get rid of that. So for now I'm going to take equation 1, and I'll write it here, equation 1, and I will get 6x plus 2y minus 4z equals 20. And then I'm just rewriting down equation 2, which is 6x minus 2y plus z equals a negative 2. Now you need to decide if you're going to add or subtract these in order to eliminate y. And hopefully you can tell that you're going to add them because your signs are different for 2. So you have 6x plus 6x. Well, that gets you 12x. Your y's you have eliminated. And then now you have negative 4z plus a z, and that would be negative 3z. And on the right-hand side, you have 20 minus 2, which is 18. And remember, this is an important part to call this your new equation 1. All right, so we have one new equation in only 2 variables. So now I need to pick another 2 equations from our system, and I need to eliminate the y variable as well. So I'm going to pick equation 2 and equation 3 this time. And in order to eliminate y, I need to multiply equation 2 by 2. So let's go up here and I'll do that. And I'll write it down. So this is equation 2, the original, multiplied by 2. I get 12x minus 4y plus 2z equaling a negative 4. And equation 3 I am just rewriting down. The next step is to figure out whether I'm going to add these or subtract them. And because they are different signs again, I'm going to add them to have my y's eliminate. When I add them, I get 13x. My y's have eliminated. I get 2 plus 3z, which is going to be 5z. And on the right-hand side, I get 3. And this is new equation 2. So looking at the green equation 1 and equation 2, I need those to eliminate one of my variables, and you can pick whether it's going to be the x or the z. So I am going to choose to eliminate the z's, and I have a 5z here and a negative 3z here, and so I will just multiply 5 times this equation and 3 times that one. So just for a note, I will write down that I am taking 5 times my new equation 1, and then I'm going to be taking 3 times my new equation 2. So going back to equation 1 and multiplying it by 5, I would end up with 60x minus 15z equals 90. And multiplying 3 times new equation 2, I get 39x plus 15z equals 9. Now in order to eliminate the z's, I would need to add these two equations together. And you end up with, I'll do this in black I guess, that you get 99x equals 99, and then when you simplify, x equals 1. So not a very scary solution at all. So now you have one of your variables, and you need to pick either your new equation 1 or your new equation 2 to substitute it into. And I will pick equation 1. And so I really have 12 times x, which is 1, minus 3z equals 18. And so then I get 12, and I would subtract that for both sides. And so you get negative 3z equals 6. And solving, you get z equals a negative 2. 2 down, 1 to go. Decide which original equation you want to substitute these into. And just looking at it, I guess I'll pick equation 1. It doesn't really matter. And so I will say I have 3 times x, which was 1, sorry about the colors, plus y, which I don't know yet, minus 2 times z, which is a negative 2, and that equals 10. So that ends up with 3 plus y plus 4 equals 10. 3 plus 4 is 7. Subtract that from both sides, and you get that y equals 3. So in the boxes, you now have your new coordinate triple, and you write those down as a coordinate point. So you have 1, and then y is 3, watch out for the order, and z is a negative 2. And this would be your final answer for the coordinate triple that makes these three equations true, or where they intersect. They intersect at that one point. The next two examples are special situations. This first one here is solving a three-variable system that will end up having no solution. And the thing to remember is you'll have no solution if you ever get a false equation. So I'm just going to write that down for your notes. Oops, if you get a false equation. And I'll show you what I mean by that. So you have three equations, 1, 2, and 3. And let's just, for this time around, try to eliminate z. All right, so I'm going to look at equation 1 and equation 2, and if I wanted to eliminate z, I would have to multiply equation 1 by 3. So I will take equation 1 and get 3x plus 3y minus 3z equals 6, and equation 2 stays as 3x plus 3y minus 3z equals 8. And in order to eliminate z, I would need to subtract these. All right, so 3x minus 3x, well, look what happens. The x ends up getting eliminated too. So move over to the y's. 3y minus 3y, those get eliminated too. And so then you end up with negative 3z minus a negative 3z. Those end up being eliminated as well. So right off the bat, you end up with 0 on your left side and a negative 2 on your right side, and that is just plain false and can't happen. And so you would say that your original system has no solution. And go back to that first slide and see what that picture looks like again. There's three situations where your three equations would have no solution. And that's it for that one. So let's move down and look at the next example. Here you're solving a three-variable system, but this time, as the directions say, you're going to end up with many solutions. So looking at the three equations, you still have to pick one to eliminate, and just to keep myself straight, I'm going to write down that I'm going to eliminate y. And in order to do that, I'm going to look at equation 1 and equation 2, and I don't need to do anything special to them, so I will just write them back down. There's equation 1 and equation 2, x minus y plus z equals 6. And I am going to subtract these, or actually no, I'm eliminating y, so I'm going to add them. And so you end up with 2x, y's are eliminated, and 2z equals 12. And remember, we give that a name, new equation 1. So now I'm going to look at equation 2 and equation 3, still eliminating y, and again, I don't have to do anything special to them. They already have the same coefficients for y, and that equals 24. So in order to get rid of those, I'm going to add again, and I end up with 5x plus 5z equals 30. And that is your new equation 2. So taking new equation 1 and new equation 2 and looking at them, I have to pick a variable to eliminate. And so if I wanted to eliminate, say, x, I would need my coefficients to be the same. So I would multiply this by 5 and that one by 10. And maybe I'll just do it right here on there. I'm going to multiply this by 5. And I would multiply this equation by 2. And so now I have new equation 1 is 10x plus 10z equals 60, and new equation 2 is 10x plus 10z equals 60. And if you notice right away, you end up with both equations being the same. And so really, if we try to eliminate, we'd get 0 equals 0, and this is actually called the identity when something is itself. And so for this one, you really have lines that are identical, and so you would have infinitely many solutions. Your coordinate triplet could be any number, and it would be true for all three of these. Okay, here's 2 guided practice problems. I left you plenty of white space, so go ahead and write and try to figure out what kind of solutions you would get for these 2. And when you're done, come on back and we'll see if we got the same answers. Remember, they'll look different because we're choosing to eliminate different variables, but go ahead and try these 2 on your own. Alrighty, here are the answers. Well, my answers. I chose to eliminate z for both of them, and hopefully I tried to communicate what I did, the process, but either way, you should have ended up with no solution for guided practice number 2. In guided practice number 3, you would have ended up with the identity, and therefore there's infinite number of solutions, and you really had the same lines there. All right, let's move on and solve one more system, but this time we're going to use it with substitution. Here's a word problem, kind of a real-life problem that involves solving a system using substitution. It says the marketing department of a company has a budget of $30,000 for advertising. A television ad costs $1,000, a radio ad costs $200, and a newspaper ad costs $500. The department wants to run 60 ads per month and have as many radio ads as television and newspaper ads combined. How many of each type of ad should the department run each month? Well, the words alone would scare you, but thank goodness they wrote the 3 equations for you. The linear systems are written for you. So they said x is the number of TV ads, and y is the number of radio ads, and z is the number of newspaper ads. It's the same idea. We have to decide, instead of this time we're not going to decide what we're eliminating, but this one looks so obvious right here because it's isolating y that it looks like we just want to substitute that in. So what we're going to do is take equation 1 and we're going to substitute this in, and eventually we'll take equation 2 and substitute that in as well, and you'll have 2 equations and 2 unknowns. So let's substitute x plus z in for y in equations 1 and 2. That is our plan. So I will start off with equation 1, and I have x, but instead of y, I will substitute in x plus z, and I only put parentheses around it so you can see the substitution. They don't really do anything. Then combine like terms. You can see you have 2x plus 2z, and that equals 60. Well, this here is an equation written in two variables, so that is your new equation 1. Just like we had new equation 1 with elimination, we have it as well with substitution. Equation 2. I will substitute in y. This time I have 1000x plus 200 times y, which is x plus z, plus 500z equals 30,000. And then you would distribute, get your 200x plus 200z plus 500z equals 30,000. And combining like terms, you get 1,200x plus 700z equals 30,000. And that is your new equation 2. All right, so now I need, maybe I'll put a little squiggly under this and this equation to go together and eliminate. So if I wanted to eliminate a variable now, I would need to multiply by something. So I'm going to take equation 1 and I'm going to multiply it by 600. Okay, so my new equation 1 multiplied by 600 would give me 1200x plus 1200z equals 36,000. And then from it I would subtract eventually my new equation 2. Another 0 in there. So this is coming from here, and that is coming from there. And in order to eliminate the x's, then I'm going to subtract. All right, and I will try to get a blue here so I can change the color. All right, and then your x's are gone. You subtract z, and you get 500z and 6,000 on the right side, and find out that z equals 12. So we have one of our new one of our variables. And so I will take that and substitute it into any of the equations, but I'm going to substitute it into equation 1. And so I would get, actually I'm going to substitute it into new equation 1, so let me fix that. But honestly, it really doesn't matter. It's just what I had on my paper, and I don't want to screw up my math. So there we have that, and then solving for x, we end up with x equals 18, our second variable out of the 3. And then I am going to use equation 3 and substitute x and y, or x and z in, and y will come right out. So in equation 3, we had y equals x, which is 18, plus z, which is 12, and so y is 30. And remember, please, to write it as the triple. It is a coordinate triple. 30 is y and z is 12. Try not to get those out of order. All right, well, you did it. Thanks for listening and flying with me today. And remember, you can pause this video and go back and watch whatever parts you need to and practice and study from it.